All right, so in this session, we are going to show you how to do the partitioning using Apache Spark. I'm Sandeep Giri, and this is going to be a hands-on session on Spark partitioning. All right. So as part of this hands-on, we will learn what it means by Apache Spark. An Oddity has partitions, and each partition has records. How to place the records in various partitions is controlled by something called partitioning. Partitioning is basically about choosing the distribution of keys in RDD partitions. That also means that your RDD partition, your RDDs must be key value RDDs because it depends on keys. This is sometimes, as in the partitioning is sometimes needed as part of your project objectives, or it is sometimes needed for optimizations. Let us take an example. At CloudX Lab, you can use Spark Shell command. You can also run other versions of Spark using /user folders installations. Okay, let me show you what it means by. So before starting, let's start our Spark. Let's go to my lab. Let's go to my lab and then we'll start our Spark Shell. Okay, let me go to my lab, go to the credentials, open the web console, and then take the login and paste it here, then copy paste the password. All right, so here we are, and all right, let me just try to, okay, good. All right, so now we are logged into the console. Either we could use usual Spark Shell, or we could use something like /user/spark, and there are these versions: Spark 2. Spark 1.2.1, 1.6, 2.1.0, and 2.0.2, and 2.2.0. These are the various versions of Spark installed, but for time being, we'll just go with default installation of Spark. What is Spark Shell? Spark Shell is basically Scala shell with which you can interact with Spark. A shell is a common word to have the read, evaluate, and print loop, REPL. Like, for example, bash is a shell whereby we type a command, it gives the output. In the same way, Spark shell will take the input from you, the commands, the program from you, and then give you the output. All right, let's start Spark shell. So Spark shell is trying to initialize the Spark, and it's trying to launch the Spark UI at this port, okay, and also connecting to the other parts. All right. So here we are. It has started the Scala prompt. You can see the Scala prompt. So it's basically a Scala shell along with the variables that point to Spark, such as SC and SQL context. All right. If you've already used it, you will be comfortable with it by now. Now, this one is which version? This is 1.5.2. Okay, if you want to use another version, you could go to /user/spark 2.0.2/bin/spark shell. Okay, but for time being, we're going to use this one. And since we have not specified the master URL while launching Spark, when we launched the Spark shell, we did not provide master URL. It's starting in the local or standalone mode. Okay. All right, so here we are. So this is the Scala shell where most of our work will go on. So first of all, let's create a normal list of numbers. Normal list of numbers. Nums is a normal Scala range. Okay, it's a Scala list. You can think of it like. And then let's create an RDD out of it. How do we create RDD out of an in-memory object? By using parallelize. SC is our gateway to Spark. This SC means Spark context, and SC provides a method called parallelize, using which it can convert a list of numbers into an oddity. Okay, so this oddity is basically the parallelized collection, and it represents this range on Spark. Okay, so oddity is nothing but um, so oddity is nothing but bunch of records in different partitions. All right, so let's to find out how many partitions does it have, either we could use partitions.length, right? It shows that there are 4 partitions. Now the other way could have been that we save this nums RDD into um, say HDFS using nums RDD.save as text file, and provide here nums RDD hands-on. Okay, this is the folder that we are creating in the HDFS. So it has successfully saved it, and let's check what has gone in the HDFS. All right, so let's open Hive. Either from console we could use Hadoop FS -ls, or we could go to Hive and go to the file browser and open that folder. Okay, so if we sort by date in ascending order, descending order, we will have this there will be a folder with the name that you provided in the argument. Here we provided this as argument, so it has created a folder with that name. In that folder you have 4 partitions, right? Why 4 partition? Big, sorry, why 4 files in that folder? Yes, the these number of files are basically coming one per partition. So there are 4 partitions in our RDD, as I showed you using partition length. There are 4 partitions, and these files are per partition. When we save as text file on an RDD, 1 file is created per partition. So what you see here is the first partition is 1 and 2. All right. The second partition is 3, 4, 5, right? And third partition is 8, as in last partition is 8, 9, 10. I missed the previous one, this one, and so on. So from 1 to 10, this is what you get. This is, you got these many partitions. All right, now let's go back here. So this was a long way of checking what's there in the partitions. A quicker way could have been using say glob. Okay, glob dot collect. Okay, so what does glob dot collect do? It basically okay, glob basically brings all the values of a partition together. Okay, so let me see if why the glob function is not working. Okay, let me see. Probably we'll have to create glom, not glob, sorry. It's called glom. So let's check with glom. Glom basically brings, so we can check the number of partitions using glom function, and glom basically brings all the elements of a partition together into an array. All right, let's take a look at it. So after glom, we are calling collect. Here, it has become, the output is array of arrays. Each array represents one partition. Okay, this method is inefficient because in case your nums RDD is really big, this will overflow your shell's memory. Okay, the data could be really big, and when you collect something, it brings everything into the local memory. Okay, so here you have these many partitions. All right, so you can see that first partition had 1, 2, second one had 3, 4, 5, fourth one has 6, 7, and last one has 8, 9, 10. Right? So this way we can quickly take a look at the partitions. All right, now before starting to do the partitioning, we must convert an RDD into a key value pair RDD. So how do you do that? We could use the map function basically converts this into a tuple. All right, here it is little wrong, the code is little wrong, so we'll have to change it like this. Okay, so what we are doing is we are calling map with our function, this one. This is basically a lambda function which basically creates tuples with the actual value comma 1. Okay, so KV is a key value RDD. Okay, so to take a look at what's there inside it, we can say take 10. Okay, so you can see that it's an RDD made up of records. Okay, it has 10. When we say take 10, it brings 10 records. So this is what we have here. All right, so now we have successfully created an RDD, a key value RDD from our original key or original RDD. Our original RDD has only 1, 2, 3, 4 up to 10. Right, now let's do the partitioning of it. There are basically two kinds of partitioner. One is hash partitioner, other is range partitioner. Let me show you the hash partitioner. Hash partitioner kind of puts the record in round robin fashion in various partitions. So first element goes to first partition, second element goes to second partition, third goes to the third partition, and if there are only 3 partitions, then the fourth element will go to the first partition. That's what happens in case of hash partitioner. I'm going to show you this. Okay, so let's use this. Let's say we have KV, RDD, and partition by, and then new hash partitioner. Here there are 3 partitions. Okay, so let's take a look what happens here. So we created PRDD, and let's take a look at the 10 records. So you see here is an interesting thing, but you can't figure out which partition contains what. For that, what we're going to do is we are going to say glom and then collect. Okay, so you see here it has converted the first, this is first partition, this is second partition, and this is third partition. All right, on what basis did it redistribute the keys? It computed the hash value and then divided by number of partitions, and based on the remainder of that division, it rearranged the partitions. So if you take a look at this one, the first partition contains all the numbers that are divisible by 3. So it basically divides the each key by each key by the number of partitions that we passed as 3, right? You remember that? So we passed 3 as argument here. So we are repartitioning KVRDD, and we are repartitioning using hash partitioner. So what hash partitioner did was it divided all the numbers by 3, and all those which resulted in 0 as remainder went to the first partition. Then all those which resulted in 1 as remainder, if you divide 1 by 3, it is 1. 1 is the remainder, and then 4 by 3 means 1 will be left as indivisible. Okay, so and similarly 7 by 3 is 1, 3 into 2 is 6, and 1 is remainder, and 3 into 3 is 9, and 1 is remainder. So this one goes as the first partition. Now the third partition contains all the numbers where remainder was 2. Okay, so you can see that the 2 by 3 is remainder is 2, 5 by 3 is remainder is 2, and 6 by 3 is, and 8 by 3 remainder is 2. So this is how we are able to redistribute elements in kind of round robin fashion. So if I say partition by 5, okay, partition by 5, what will happen is it will create these many buckets. So it created 5 partitions. It created 5 partitions because we passed 5 as argument. The first one contains all the elements where remainder was 0. 5 by 5 is remainder is 0 to 10 by 5 remainder is 0 and so on. So similarly 1 remainder, 2 remainder, 3 remainder, 4 remainder, right? So that's the magic of hash partitioner. So with hash partitioner, you can distribute the keys kind of equally into the buckets. Okay, this is great when you want to improve the performance by equally distributing the work amongst many partitions. All right, so now next one is using the, all right, so next one we are going to use another function. So where we are going to show you what does it mean by range partitioner. Okay, so even though here what you see is when we save an RDD like this one, what would happen is it'll have so many elements, right? And the ranges is kind of overlapping. Range means from what element to what element is contained in an RDD. So ranges are absolutely overlapping, right? so so in case you want to keep a partitioner such that the ranges do not overlap, meaning we want to say that from this point to this point give it to this particular partition, and from this point to that point we give it to the other partition, and the two ranges, two parts are not overlapping. Okay, so in those cases we use range partition. I'm going to show you this. Imagine that you have this list of words. Also, please note that we'll have to import the partitioner. I'm going to import it first, and then we'll talk about the rest of the things. Okay, so let's say we have a list of words. Let's say we have list of words. Okay, we have list of words like this, right? And you want to create two partitions out of it, such that if both of the partitions are ordered and you concatenate them, it will give you the answer, right? If you give it will give you the answer, and that's where the range partitions come into play. Or let's say you're dividing the work and you know that you want to operate on all the numbers from a point to point in using one partition, and all the numbers from one point to another point in another partition. All right, so in that case you can use the range partitioner. All right, so range partitioner is an interesting phenomena, and so what we do here is we first of all defined we created words RDD by parallelizing a local array, and this local array contains these many words. And once we are done with that, we're going to convert this local array into a key value RDD. All right. So words.tuples is a key value RDD. Just to take a look at one value of this RDD, you can see that it is this comma 1. Now, you could have any value, just it so happens that in our examples, we don't need value too much. The key is good enough. Therefore, we have just put 1 here. Okay. Next is we are calling, next is we called words.partition by, and we're passing the range partitioner. An instance of range partitioner with two arguments. First one is the number of partitions that we wish to create, and second is the same RDD as words.tupes. Okay, here why we are passing it here. Basically, this range partitioner, what it's going to do is it's going to sample your RDD. Therefore, this class must have access to your RDD. It is going to call sample on your RDD, find out few random numbers or random strings, and based on that it is going to figure out that how big is your data, and based on that how is your data spread out, and based on that it's going to partition the things. All right, so here we are. So it has created an output RDD. Let's take a look at output RDD. It's a shuffled RDD, and when we say glom dot collect. Again, why we are using glom? So that we can combine together all the elements of a partition into an array. So this is one partition and this is another partition. Now please pay attention to it. It has figured out that if it divides the words such that all the values which are smaller than I go in the first partition and all the values bigger than I go in the second partition, the balance would be great. So this is done using sampling. It figured out that if it parts the data based on I will be great. So if you'll take a look at it here, all these words are either smaller are starting with a character that is either smaller than I or equal to I, while all the values in the second partition, all the values in the second partition from here to here, they're starting with the character that's bigger than I. Okay, when I say bigger or smaller in terms of character, it means that alphabetically it comes after that. So if I say some character is bigger than I, that means it's J, K, L, M, N, O, right? So you can see that using range partition, we are able to partition elements such that each individual part is lesser than a particular key and the other part is bigger than that key. Okay. And we don't have to define that pivot point, that point, the key on which it's parted. It is automatically figured out by this function called by the range partitioner. All right. So to take a closer look at this, we could save the result in HDFS and take a look at it. All right. So we could say output.save as text file, and we could provide the directory here. Okay. So this directory already exists. That's why I'm getting this error. So we could go to this folder. All right, and delete those directories and go back to the folder again and go back to the console again and try this again. So here what you get is a folder with that name. Okay, you see my output directory. It has two parts, part 0 and part 1. All right, you can see that. And part 1 is this. All right, so this is the way we can divide the key value pair Oddity into ranges. Right? Here, all the things that are there are bigger than I. Here, in the first partition, all of the elements that are here are lesser than I or equal to I. You can see I, A, C, I, A, C, E. Right? So this is how we do the partitioning in Spark.